how to evaluate the twist of each contact on the object and the twist on each contact on the hand. Now let's see what we get when we put together these two twists through the contact. So the first thing that we can do is to evaluate the relative twist at the contact as the difference between the twist that I have on the hand minus the twist that I have on the object. This difference describes the relative motion that I have at the contact. So the contact model constrains some components of this relative twist, locking some part of the motion. And the type of a constraint depends on the type of contact that I have. In our model, we usually consider three types of contact models that are the single point without friction, the single point with friction, and the so-called soft finger. So the single point without friction is used when I have hard surfaces, for example steel or other types of metal, with a low or without friction, for example a slippery surface with a lubricant and so on. So this is used when I have a smooth surface with a smooth and a hard surface with very low friction. The single point with friction, that is sometimes called hard finger, is used when I have a hard surface but I have friction, for example hard steel surface but with a roughness that allows to have a higher level of friction. And finally, the soft finger model is used when the contact surfaces are not very hard. So when I have the contact, I have a local deformation of the surfaces. And actually, in this type of modeling, the contact is not more a point, but is a small surface. And this is typical, for example, when I consider soft materials like rubber, but also in biomechanic models of the hand, because our hand is of course is composed of muscle, skin, so that is deformable. So the soft finger has to be used in this case when I have a soft surface, for the finger and or for the object. In all these three cases, what we do is to limit some components of this relative twist, and we do this by using a matrix, a selection matrix HI, that I multiply by the relative twist. So with this matrix I select some components of the relative twist, and I set them equal to 0. The dimension of HI matrix depends on the type of a contact that I choose. So this matrix HI, its dimension are Li minus times 6, where Li depends on contact model. So this is what we do for the kinematics of the contact. So in the kinematics of the contact, we constrain some parts of the relative twist. Physically, what happens in the contact is that there is a local deformation of these contact surfaces, on which we have a pressure distribution that leads to a contact action that can be a force or a force and a torque. We will see. And yeah, so the parallel aspect of the contact, beside the constraint, is the force that we obtain in the contact. So at each contact we can define a twist lambda tilde I. This a wrench, sorry. This is a wrench, so it's composed of a force and a moment. What is different for each contact model is the components of this wrench that is different from 0. So the components of this wrench that are different from 0 depends on the type of contact point that we of contact model that we choose for each point. And so for each contact we will have a subset of contact forces that are different from 0. This is a smaller vector than lambda tilde I, whose dimension also in this case depends on the type of contact, so it is Li. So for example, if my contact model limits only one component of motion, I will get only one component of force as a reaction. And yeah, I can relate the complete contact wrench to the components that are different from 0 through the transpose of the H matrix that we have used to define the relative constraint twist. Okay, this will be more clear, I think, when we will see more deeply each contact type. Let's analyze, for example, the first contact model that we saw, the single point without friction. So in this case we have a contact between hard surfaces and without friction. So what we have, for example, let's consider the finger surface that for simplicity I draw like a line, and the object surface, more or less, they are touching in this point Ci, and in this contact model I consider a single point without friction. And what is the this mean that in this friction I can slide the surfaces each other. So I can slide in the tangential direction. I cannot, of course, rotate in three directions. What I cannot do is this type of motion. This is the constraint relative motion, because this is limited by the contact between the surfaces. So in this case, what if I consider the relative twist, I have to constrain the first part, since I have defined the twist with respect to the contact point reference frame whose x-axis is the normal. What I have to do is to take from this relation the first row and set it equal to 0. So I multiply this by hi, I set it equal to 0, and in this case I have that hi is only a row with 1 and the other elements are 0, and so li is 1, the dimension of our constraint is 1, because I take only one of these components and I take it equal to 0, and this component is the motion in the relative in the direction orthogonal to the contact surfaces. And yeah, so I have only one constraint. Then I will have, as we said before, only one component different from 0 of the contact branch. In fact, in this case, the contact can apply a force. The force that I can apply is only in the normal direction, because I have not friction, so I can apply only normal forces. So my total contact branch will be a certain normal force, and the other 5 elements will be 0. And there is another constraint that I have to satisfy, that is that the normal force has to be greater than 0, because the contact is a unilateral constraint, so it cannot work in both the directions. So I can pull the surface each other, okay, without breaking somehow the contact. So this is the condition that I have to satisfy to maintain the contact. Okay. The second contact model that we see is the single point with friction, that is called also hard finger. The hard finger model, so again let's consider a finger surface, object surface, the contact here, and in this case there is friction, so also the motion in the translation in the tangential direction is constrained by the friction. We have, as in the previous case, the translation in the normal direction is forbidden. What we have in this case, what we can do is just rotating with respect to the contact. So in this case, HI the components that I choose to set them equal to 0 are the three translational components. So HI will be, the first part will be an identity 3 by 3 matrix. The second part will be a 0 matrix 3 by 3. So Li will be equal to 3. And yeah, concerning the contact branch, I have that in this case I can apply through the contact a three-dimensional force because I have both a normal component and a tangential one. So I have the normal component, the two tangential components, and through the contact I don't apply torques. So this is the contact wrench in this case. Of course, these three components are not free because they are limited by the friction of the surface. And yeah, the simpler model that we can consider is the Coulomb friction model that limits the ratio between the tangential component and the normal one. So yeah, we have also in this case the constraint that the normal component has to be greater than 0. But in this case we have also that the tangential component, so this has to be lower or equal to the normal component multiplied by this coefficient, that is the friction coefficient between the contact surfaces, that depends on the contact properties, for example, on the material, on the state of the surface, on the roughness, and so on. So this depends on the condition of the materials. And yeah, this contact model has also quite nice graphical representation, because if I consider this is the finger, this is the object, if I consider the normal direction and I draw a cone here with an angle phi that is the arcotangent of I. So this angle depends on the friction. So what I have to satisfy these two conditions, I have this force has to stay inside this cone. This cone is called friction cone. And yeah, that's it. Okay, the last contact model that we consider is the soft finger. So let's again draw the finger, the object, the contact. And in this case, what happens is that since the surface is not soft, we have that locally we get a deformation. So if I zoom somehow this area, I see that the contact is not a point, but it's a small area. So what I have is that I have not a contact force, but a pressure distribution whose resultant is not more a single force, but gives also a torque component. So in this case, what I constrain is through the friction, the translational motion, of course the motion in the tangential and normal direction, but in this case I constrain also the rotation in this in the direction normal to the surface. So what I get here is that in this case HI is I lock, I don't know, is of course I lock the translation in the contact point, but also I constrain the rotation with respect to the direction normal to the surface, and of course the other two rotations are free. So practical example, if I have this piece of paper, of course if I have a hard finger model, I don't constrain the rotation. If I consider a soft model for the contact, I constrain the rotation. Okay. In this case, I have that Li is 4, and then the contact wrench is a normal force, two tangential components, and a component of a torque in the normal direction, and that's it. This is the lambda vector for the soft finger contact model. Okay. I can write the contact constraints for each of the contacts, so for all the contact points, and so I have H1 multiplied by the relative twist at the first, zero, H2, etc. And at the end, I can collect all these constraints equation in a unique vector in a unique expression that is H multiplied by equal to 0. So this matrix H is composed by combining in blocks the HI matrices. And okay, this expression summarizes all the constraints for all the contacts. Recalling what we got from the kinematic study, we can write that the twist on the hand is given by the the complete Jacobian matrix multiplied by Q dot minus. This is related to the twist of the object through the transpose of the complete Grasp matrix. And finally, we can write this as J Q dot minus G transpose no equal to 0, where J H is the hand Jacobian matrix and G transpose equal to H G tilde transpose is the transpose of Grasp matrix. So these are two very important matrices in grasping, and both of them depends on, of course, the Jacobian depends on the hand, on where the contacts are, but also on the type of contact that we consider, because there is the matrix H that takes into account also the type of contact that we are modeling. The same for the Grasp matrix. The Grasp matrix takes into account the contact point locations, but also the type of contact points through the matrix H. Okay.